we're going to talk about heat capacity and calorimetry. So let's review heat really quick. Remember that heat is the energy that is transferred between two substances due to a difference in temperature. So it will always go from the substance with a higher temperature towards the substance with a lower temperature until it reaches thermal equilibrium and at the same temperature. There's a few different units that we can use for heat. We can use joules, and therefore kilojoules, right? And that's the SI unit. But we also have calories. And calories is useful because it's water-based, and that's how your food is measured, right, in calories. So when you're looking at a food and nutrition label, the amount of calories is literally the amount of energy that is being provided from the food. So on actual food labels, it's typically uppercase C calorie, although sometimes it's not written that way. But that means that one calorie on a food label is equal to 1,000 lowercase c calories. So really they're kcal. And some countries will actually label it kcal instead of calories, but not in the US. So, but some countries actually use joules and kilojoules on their food labels instead. So it's just a way that we measure it. And the conversion here is that 4.184 joules is equal to 1 lowercase c calories. And this is an important value for water. So this is what we call the specific heat capacity for water, and it's the amount of energy it takes to raise 1 gram of water by 1 degree Celsius. So that's why 1 calorie it's water-based, because it's specifically the amount of energy to change the temperature of water. Which, most of our systems are water-based, so it winds up being a useful unit. Just make sure you can convert between the two using this conversion here. So let's get a little bit more specific with heat. And I say specific because we're going to get into specific heat capacity. So specific heat capacity is the amount of heat it takes to raise 1 gram of a substance, raise the temperature by 1 degree Celsius, or 1 Kelvin. Remember that the size of a degree Celsius and the size of a Kelvin is the same. It's just shifted upward for Kelvin because there's no negative numbers. But it is very specific for 1 gram of the substance and 1 degree Celsius. It allows us to very easily compare the amount of heat it takes to change the temperature between multiple substances. So that's why specific heat capacity is useful. We usually use lowercase c for specific heat capacity. I've occasionally seen S, but I'll use C. And now, so water has a really high specific heat capacity. Liquid water's specific heat capacity is 4.184, which we talked about on the previous slide. And it's joules per gram Celsius. So that's the number of joules it takes for 1 gram of it to change by 1 degree Celsius. It would also be, you could also write it joules per gram Kelvin. It's the same thing. And so that's for liquid water. Now the specific heat capacity will be different for solid, liquid, gas because it will take a different amount of energy to change the temperature depending on the state of matter it is. So you need to be very specific for that heat capacity. Now we say specific heat capacity, but we also have just something called heat capacity. And heat capacity is just the heat it takes to change the temperature by 1 degree Celsius. It is not specific for the amount. So specific heat capacity is mass dependent. Heat capacity is not. So you might have, if you have like a beaker with 50 grams of water versus a beaker of 100 grams of water, it's going to take more heat to change the temperature of 100 grams of water than it will take to change the temperature of 50 grams of water. So the 100 grams of water has a greater heat capacity than the 50 grams of water. But because they're both water, they have the same specific heat capacity. The general heat capacity, this doesn't come up a whole lot. Just know that it's going to take more energy when you have more of the stuff. But for the most part, we're going to use specific heat capacity. Okay, so calorimetry. Literally calorie measuring. Okay, so it's how we measure the energy changes for reactions or processes. And we use a calorimeter to do that. Calorimeters should be insulated as best possible. So this one is what we would call a coffee cup calorimeter, where you have two styrofoam cups kind of nested together, and the styrofoam acts as an insulator. It will typically be in a water-based system, and you'll have a thermometer to measure the energy change, and you might have some kind of stir. That's optional, but you might have it. And hopefully it's covered as well, so again, to insulate. The biggest source of error whenever you're doing a calorimetry lab is heat loss to the surroundings. Whenever your reaction is happening, you want the thermometer to pick up the temperature change for like all of the heat. So for example, if you have an exothermic reaction, you want all of the heat to go into the water so you can accurately measure the change in temperature of the water. If you lose heat to the surroundings, going out from the cup, then the water will not change temperature as much. So you will not notice, you will not calculate as big of a heat change because you've lost some heat to the surroundings. So you need to be careful there. That's the most important source of error that you should talk about whenever you're doing a calorimetry lab. You can also have a more fancy calorimeter. So this one is called a bomb calorimeter. And a bomb just means it's a sealed container. Okay, so you have a little sealed container where the reaction will happen, and then it's surrounded by water, and you'll still measuring the temperature change of the water. Now in this case, you have ignition wires to start the reaction to provide the activation energy or to ignite it or whatever. And then use some kind of stir. You want to make sure it's stirring as much as you can, so that way the thermometer is picking up the energy change for the whole amount of water. But it works the same way. We don't have bomb calorimeters here at school. We just use coffee cup calorimeters, and we try to insulate it as best as possible. But a bomb calorimeter is really helpful when you have something that might react with water and you don't want it to react with the water. So you can just kind of isolate the reaction from the water. Now, whenever you're doing this, you want to remember that the thermometer is measuring the surroundings. It's not measuring the system itself. So if the thermometer is picking up an increase in temperature, that means that the system is losing heat. And that heat's going to the surroundings, which is read by the thermometer. So if you have an increase in temperature of the surroundings, that's exothermic. If your thermometer is picking up a decrease in temperature, that means the heat must be going into the system and away from the surroundings, and so that will be endothermic. So just be really careful there. That's a big mistake that I see sometimes is that you'll flip that around. Don't do that. The thermometer is measuring the surroundings. Okay, so the equation that we use when we're dealing with calorimetry experiments is Q equals MC delta T. A lot of people will call that Q equals MCAT, MC delta T. But Q is heat. M is usually mass because C is specific heat. And so if your mass is in grams, you want to make sure that your specific heat is in joules per gram Celsius. So the grams there will cancel. Occasionally I've seen where they'll give you the specific heat in moles. It's like joules per mole Celsius. If they give you moles for specific heat, you want to make sure you use moles for M. But that is more rare. Really just pay attention to your units, so that way you're all set. And then of course delta T is your change in temperature. And it could be in Celsius or Kelvin, it doesn't matter. Just label, if it's in Celsius, make sure that your specific heat's labeled in Celsius. If it's in Kelvin, make sure your specific heat's labeled in Kelvin. But it will be the same values because the change is the same whether it's in Celsius or Kelvin. And so you'll use that to calculate the heat based on the change in temperature. Now, when you're doing the calorimetry, remember that your thermometer is picking up the change in temperature of the surroundings, and it's usually in water. Not always, but usually. So if you are calculating for a calorimeter, the Q that you calculate, you want to use the mass of the water, the specific heat of the water, because you're measuring the change in temperature of the water. So then don't forget, if your delta T is a positive value, then that's exothermic for the reaction overall. So that means when you are calculating Q, you'll get a positive value for Q, but you need to change the sign of that to a negative value because the system is exothermic. So really pay attention to that, and we'll do some examples to make sure that we've got that down. Okay, so here's an example of a calorimetry experiment. And they did the experiment twice, once with almonds and once with cashews. And notice how they're giving you the mass of the water, the specific heat of water, the change in temperature of the water, because you're measuring the surroundings. So let's go ahead and calculate for the almonds first. One thing that you need to remember, because water's density is 1 gram per milliliter, when they give you the amount of water in milliliters, that's the same as the grams for water. So for almonds, I'm going to use Q equals MC delta T. My mass of the water is 2,000 grams. Specific heat of water, they gave us 4.184. And then subtract the change in temperature there is 18. So when you multiply, you'll get that the Q is, it's a really large number. So I'm going to go ahead and, let's see, it's 150,000 joules if I round to 2 sig figs. So I'm going to go ahead and put that in kilojoules, 150 kilojoules, just to keep it in a more reasonable value for us to work with. But then it says per gram. So I want to go ahead and divide that by the 6 grams that they give us. So we have 25.0 kilojoules per gram of almond. And that's the amount of heat energy that you get from almonds. So do you notice I didn't do anything with the sign? All right. Couple things there. So the temperature of the water is increasing. Right? Which means that when you're burning the nut, it's releasing heat, and the heat's going into the water to raise the temperature of the water. So the energy change of the nut is actually negative 150 kilojoules for those 6 grams. The difference is that because it says produces the most energy, because it says produces, I don't need to worry about the sign. Okay. Produces the most energy. It produces 25.0 kilojoules per gram. You could also say the energy change is negative 25.0 kilojoules per gram. So just be careful and make sure you're wording it properly. Let's go ahead and calculate for the cashews next. Like this, cashews. Same thing, you're going to want to use Q equals MC delta T. And my mass is, for the water, is 1,000 grams of water. My specific heat for water. And my change in temperature for the water is 28.8. So when I calculate that out, I get 120,000 joules, or 120 kilojoules. And then I can divide by the mass of the nuts to get, so for cashews, it's 24.0 kilojoules per gram. And again, that's how much energy is released per gram of cashews, but I don't need to include the negative because of how the question is worded. So if I compare those two, almonds produces more energy per gram, or releases more energy per gram. Okay, so this one's a little different. We're going to, it's still a calorimetry experiment because we're measuring the change in temperature, but we have two solutions that we're putting together and reacting. So we have 50 milliliters of HCl, 50 milliliters of NaOH. The initial temperature of both solutions was 19.8. The reaction happens, and the final temperature of the mixture was 26.3 degrees Celsius. What is the heat of reaction per mole of sodium hydroxide? So your first step, because you have a change in temperature, we want to use Q equals MC delta T. MC delta T. But since we have the change in temperature of the mixture, I need to use the total mass of the mixture. Now both of these are water solutions. Right? They're 0.5 molar solutions. So we can assume that the density is very close to the density of water. And so we've got 50 milliliters, 50 milliliters, that's 100 milliliters total, or 100 grams of our mixture. It might be just slightly off, but for our purposes, that is close enough for our calculation. We're also going to assume that the specific heat, because it's a water-based solution, the specific heat capacity is going to be very close to the specific heat capacity of water, 4.18. And then our change in temperature from 19.8 to 26.3, the change in temperature was 6.5 degrees Celsius. So if I calculate, I get 2,717 joules, or 2.72 kilojoules. It didn't say you had to put it in kilojoules, so you could have left it in joules, but it's just very common for us to put it in kilojoules. Then it wants a heat of reaction per mole. So we need to calculate the moles of NaOH. We have 0.0500 liters. Milliliters needs to change to liters. Times the molarity will give us moles of the sodium hydroxide, 0.025 moles of the NaOH. So I can divide 2.72 kilojoules over the 0.025 moles, and that will give me 108.8, so 109 with 3 sig figs, 109 kilojoules per mole for the NaOH. And so that is our heat of reaction per mole of sodium hydroxide.